record. Okay. Nice. All right, lab. So lab question. All right. Anyway, go ahead. Try to ask it or type it in, or I can share my screen, or I could go to your Canvas page if there's something I could look at there that would help.
Yeah, actually, that would actually be the best way, I think. If you went to the Canvas, went to the lab, because it's just an initial lab. So it's just the lab for, it looks like he's trying to get us to understand the lab process. And I mean, it makes sense, but I just got stuck in one part and I don't know exactly what he's asking. Yeah.
Okay, perfect. Okay, help me out here. So I went to assignments. Is that the right place to see the lab, or should I go to modules?
It should be under just under the first assignment, the first lab assignment for this week 1.
So let's see, week 1. There's something that says lab quiz, lab report.
Lab. It's going to be under
discussion.
It's going to be under lab course introduction and units.
Okay, I see discussion, course, introduction, and units.
Yep.
That it?
It should be under, yeah, it should be under the lab. It's like, let me see here.
We could share our screen and show you what we, because I have it up too.
Oh, okay. You do? Okay, let me, let's see. I think I got to give you permission here. 1 participant at a time. Oh, I think you can do it then. Yeah, go ahead.
I think Elizabeth and I have the same question, so I'll let her share the screen. I don't have it pulled up exactly.
Okay, it says host disabled participant screen sharing.
Okay, 1 participant can share at a time. Advanced sharing. Oh yeah, under advanced, I see. I got host only. Okay, so let me go all participants. See if I'm doing this right. How many participants can share at a time? 1. You think you got it?
Yeah, I can do it now. Okay. So,
good.
Yeah. This is, can you see this?
I can, and as a different question, I just wonder why I don't see that here under assignment.
I found under modules as well, so maybe it went to.
All right, I'll try modules just out of curiosity. And then, and then it's broken down by weeks. All right, looks like it's in reverse order here. Let me go all the way down to the bottom. And then I see, okay, yeah. So lab course introduction units. I see it under, yeah. Okay, but anyways, thanks for sharing yours. Okay, so.
Okay.
All right, so I mean, I guess so my problem with this, I'm not sure if it's exactly the same as Elizabeth, but I am struggling with the parts, the last couple lines of that theory section there. So this is our curve fit model for the lab. For this lab, you should find the theoretical curve fit parameters. A equals that right there. Yeah. And I mean, that kind of leads into the questions below it as well, with question 2 more specific.
Okay.
But I'm just not sure exactly what I'm supposed to write in there to put into my data analysis section of the lab report.
Okay. Let me do 2 things then, if it'll be okay with you.
Yeah.
Why don't I use, now that I found it here, I'm going to read it on my screen, but if it'll be okay, I think this might work better. You guys tell me. I'm going to share my screen.
Yeah.
And that way you can see my doodle pad. And I think between me talking and seeing me doodle, you'll get a better understanding. I just got to turn on my video camera here. Okay. And then connect it. Okay, so let that connect. And if need be, I'll come back and put this on the screen, but I think it will work better this way. you guys tell me. I want to do whatever works for you. But I'm just going to doodle here, blah, 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 blah. All right. And also, I don't want to take too much of your valuable time, but I think I can do a better job if I start back at the beginning since I haven't looked at it. So let me read the theory here where it says, in this lab, we measured the relationship between the mass and the radius. The material of the sphere stays the same. Therefore, the density should stay constant. The symbol for density is the Greek letter rho, and it is defined as. So first thing I'm going to just kind of doodle is the equation for density, mass per volume. And then knowing that, and this is the next one, it says plug the formula of the volume of the sphere into the definition. Okay, so I have mass, and then the volume is 4/3 pi r cubed. Okay, 2, using algebra to isolate mass on one side of the equation. So I'm going to move that to the other side of the equation. So I'll have mass over here, and over here I'll have 4/3 pi r cubed times rho. It says here, these steps produce this equation. All right, now, this equation then means everything else but this r is buried in an A. So if we write this as A RB cubed, what we're saying here is A should be 4/3 pi rho, and B should be 3. And let me pause and ask you, does that make sense so far?
Yeah.
Okay. Thank you, Elizabeth. Tyler, how about you? Does that make sense? Or should I backtrack?
Yeah, that makes sense.
Okay. Okay. So A and D are numbers. Okay. So this is our curve fit model. Okay. For this lab, you should find the theoretical. Okay. So there it is. So the theoretical value of A is right here. And that's what he writes, 4/3 pi rho. And the theoretical value of B is 3. Be sure to include these results in your data analysis section of your report. Now, Tyler, I'm going to go back to a question for you. You said you were having troubles with that, and there's not a question in there, but what we're, I guess, trying to say is if you were making a plot.
I guess my question for that part is that, so if you, I'm not sure if you have the canvas still up on your screen.
But if
you go up to the part where it says in the lab report instructions on the top where it says data analysis, it says that we should include a screenshot of our graph with the points all plugged in and our table filled out.
Okay.
It says below that each lab also includes physical equations to calculate theoretical values for the curve fit parameter. Data analysis should include these theoretical values and compare them to the experimental values. I don't know what that is asking me to put in, and I'm assuming it's something more than just having a screenshot of my actual table and my graph.
Yeah, okay. I think it's asking this. Let me leave this handy, but I'm going to take it off the screen for a second and start with a piece of paper, because your plot then and so this is your experimental plot. You're putting mass on the vertical axis and you're putting radius on the horizontal axis, right?
Yes, that's correct.
Okay. And I don't know if you've done this already, but when you do, or if you did, it either will look like or does look like something like this. Is that true? Have you done it?
Yeah, it's something like that. Yeah.
Okay.
I mean, the numbers are the chart where he left it up to us to put in whatever numbers we chose. So, I mean, I'm sure everyone gets different values.
Okay. Okay. So when you do a curve fit, And maybe I should ask you, what program are you guys using for the curve fit?
Desmos.
Desmos. Okay. Now, I'm not that familiar with Desmos, but I'm going to go on a limb here and say that Desmos works like all the other curve fit programs I'm familiar with. And when you put in your data and then say curve fits, you give it some instructions that say, okay, M equals, and you say that there'll be a constant A and then the variable R and then a constant B. And the computer does the curve fitting and it says A equals and it gives you a number. And then it says B equals and give you a number.
Yeah, it did that.
Okay, so you've got that far.
Mm-hmm. Would you like to use my numbers as examples?
Oh, yeah, that'd be good. What'd you get for A?
I got 6.99976.
Okay, and what'd you get for B?
3.00003.
Ooh, how many zeros was that?
4 zeros. I'm sorry. I think I might have said one too many.
40. No, yeah. Okay.
Yeah, I didn't round anything because I wasn't sure that because I didn't see anything about any sig figs or anything like that. So I just left it as it is for now.
Yeah. Now we probably should definitely round those. But okay, good. So here is what that question is asking of you. It says, now that you've done this, now that you put in your data, now that you've done your curve fit, and now that your curve fit has given you A and B, these are the A and B that you get from your experimental data. And they're saying, how does it compare with the theoretical value? Now, let me start with the easier of the two. B, the theoretical value is 3. So how does your experimental value of B, which is 3.00003, how does that compare with the theoretical value of 3?
Okay, so so that one's pretty accurate.
Extremely accurate. Yes, yeah. Yes.
And then just A is a little different. It's a little weird.
Okay, now A, to get a theoretical value, we don't have a number unless we know the density. Did somewhere in this he tell you what the material was?
No, it was. I think the material was supposed to be an unsaid material, and one of the questions on the very bottom, we're supposed to compare it to water and say whether or not it's heavy or not. There wasn't a specific.
Okay, so without knowing what the material is, we can't say how well our experimental value is to the theoretical. But what we could do, and I think this is then what you're asked to do, is to do this, is to say, take the theoretical value, the 4 pi rho, and set it equal to what you found in the experiment. And that way, you can actually then figure out what the density is experimental.
Okay, that makes sense. I see.
So I'm going to take that number, 6.9976, multiply by 3, divide by 4, divide by pi, and I get a density of 1.67. Oh, now, unit-wise, I guess I have not asked you what you plotted. Did you plot, what units did you plot mass in?
Mass was grams, I believe.
Grams?
Sorry, I keep moving my screens around. Yeah, I did that one in grams. And then it was I believe it was in centimeters.
Okay. And then centimeters.
Mm-hmm.
Okay. So your density it would be grams per cubic centimeters.
Yep.
So according to your data, hang on, let me shut my door. I got noise. I didn't want that noise to disturb you. I don't know if it was getting picked up on the microphone. But I would say this way, your experimental value of the density then, because this is it's from the experimental data, it's the curve fit of the experimental data. You then used this curve fit to figure out what the density of this is. Now, water, by the way, is 1.00 grams per cubic centimeter.
Okay, so that makes sense. That makes a lot more sense.
Yeah.
Setting it equal to the parameter was what I was missing. The work that you just did there to find that density. That's what I was lost with.
Good.
So that answers my question.
Good. How about you, Elizabeth? Did I cover your question?
So there's a question like in questions on the lab. It's like, what are the units of the curve fit parameter A? So it would be grams per centimeters cubed, right?
Yes. And to take that one step further, you can see it here. This parameter here would have the same units as this theoretical side. And so no units, and then units of density. So this thing must have the same units of density that you are using. And the density you are using would be the density of, and that's grams and centimeters.
Right. Okay.
Because this could have been done in kilograms and meters. And then the parameter would have been kilograms per cubic meter.
Right, okay.
And
so yeah, that answers my question. Yeah, okay, cool.
Good.
I'll stick around and just see if anyone else has questions that I might need. So, but thank you.
Oh, my pleasure. Yeah. In fact, I'll spring this back to both of you. Anything more on this lab before we move on to other questions?
Thank you as well. That was also very helpful for me.
Awesome.
That was all for me too.
Awesome. Okay. Hey, so a few more people here came in either as well, first time or second time. Let me say the best way for me to do things. Oh, good. And I already got a question in the chat. Is to take questions in the chat. That way, while I'm talking and explaining, I just want to make sure there's a fair line that develops. Anyway, so throw that in there. Oh, good. And then Johnny, you threw another question in there. Good. So I've got 2 in here so far from 122. And so again, I'll just tell everybody, as you come in, you got a question, throw it right into the a chat so I can keep things in an orderly fashion. Now, there's one exception to that, and hopefully I made it clear, probably not that clear, but so I'm going to clarify again. During special times, and for this moment in time from, let's see, 12:30 to about 1:15 or however far we need it, I give special priority to you guys in 121. And so unless I see a 121 question up there, I'm going to jump into the 122 questions and start working on that. So I'll give another second or two if anybody's got a 121 question to throw that up there. And while I give that a chance, I'll reorganize and start writing here. Let's see, chapter 23, number 13 here, coming from Brendan. And let me write that 122 number 23. So when I send out a recording later on, I can kind of say, okay, this started 20 minutes into the recording, roughly. Nice. All right. So let me jump on this. I don't see any other 121 questions, and I'm gonna jump into this. Let me just use my other screen here and flip from my. This is Canvas. Let me get to the questions. Let me read number 13, and I'll just read it out loud for you 122 people here. It says, what are the magnitude and the direction of the electric field that balances the weight of A, an electron, and B, a proton? All right, so I'm going to put A here because we're looking to balance an electron. And then maybe down here, I'll put B. We're trying to balance a proton, okay? And if you look carefully at this question, the question says, what is the magnitude and direction? And I'm gonna start with direction. Let me come back up here. This was I was gonna say main, and I guess it's the main, one of the main. They fit together. This whole chapter, this first chapter was on the electric field. That was the title of the chapter. And if you take the electric field and multiply it by the charge, so you have a particular charge and you place it in an electric field, the multiplication of those two together gives you the force. Now, here's why that's important. Because Q can be positive or Q can be negative. Now, watch what happens when it's positive. When it's positive, you would be then taking a positive charge and multiplying it by the field. So that's a positive number multiplied by the field. Let me just say the field is 1 for a second. And if I take a positive number like 5 and I multiply it by 1, I get 5. Let me not worry about the number, but I get a positive. So if the field is positive, because you multiplied by a positive, the force will be positive. And that's another way of saying, if I can use one of my favorite phrases, reading the math, you're basically saying that the direction of the force and the direction of the field are the same if Q is positive. But watch what happens if Q is negative. Now, if Q is negative, let's say this is, say, a negative 5, and the field is still a positive 1. Now I have a negative 5 times a positive 1. The result is a negative 5. And let me not worry about the 5, but it's negative. It's opposite of the field. So the force is opposite of the field when you have a negative. Okay, so I'm going to use that information because here, if I drew a picture of an electron, gravity pulls it down, mg. Now, down here, if I draw the picture of a proton, again, gravity pulls it down, mg. In order to balance the electron, I need the electrical force to be up, and also to balance the proton, I need the electrical force to be up. But here is an important part of this problem. And I don't know if the orange will show up. It's kind of an orange or a burnt orange. Your textbook, let me just double check again. I think I looked this up last time. I thought the author liked to use, he likes to use kind of this orange, burnt orange color for electric field. So maybe to help distinguish force from field, I'll change colors. It's not going to be that much different. I want to be consistent with him. But here's what I'm trying to say. I'm trying to say then that from what I've said so far, I would have to conclude that the electric field is down. And so it is down for the electron. Because again, I want the force up. And again, as we said, force and field are opposite for the negative charges. Now, for the proton, that means the field would have to be up. Because, again, mentioned earlier, the field and the force are in the same direction if Q is positive. So when this problem asks for both the direction and the magnitude, starting here with direction, I've got for the A, the field has to be down, and for B, the field has to be up. And that's, I think, half of what this problem is getting at, is trying to convince you and make you realize this little subtlety between the direction of the field and the direction of the force. So if you had a field, you know, say to the, I'll go on the screen to the right, then if you put a charge there, let's say this is a charge, and the charge is positive, it would move to the right, but if the charge is negative, it would move to the left. So the direction of the force is different for a positive compared to a negative, opposite directions. So that's what that math is saying here, and that's the realization. Okay, so now the other half of this problem is saying, well, you want these two to balance, so we're trying to say that the magnitude of the electrical force pushing it up is equal to the magnitude of the gravitational force pushing it down. So if you just let me write mg here without any negatives down, and then here for the magnitude of the force, I'll just do magnitude of Q times the magnitude of the field. So if I go to solve this, let's see, we're after the field. So the magnitude of the field is equal to mg over the magnitude of the charge. So now I can get a number here by grabbing my calculator and say, okay, so what is the mass of the electron? Now they say go ahead and use table 23.1, and that's fine. I'm going to assume that table, I can look it up here, but I think they give us the mass of the electron as 9.11 times 10 to the negative 31. G, well, that's last semester. That's probably not in the table. So that's 9.8, or it's in physics 121. For some of you, that's last semester. For others of you, that's 2 semesters ago, or 3 or 4, yeah. And then divide by the charge of the electron. So the charge is 1.602 times 10 to the negative 19. So this would come out to be 5.57 times 10 to the negative 11. And let me look at the units. Mass in kilograms times acceleration meters per second squared is a Newton. So the top has a Newton and the bottom has coulombs. And so this is the answer, newtons per coulomb, which is good because that is the appropriate units for an electric field. Electric field are measured in newtons per coulomb. So there is the value of the magnitude of the electric field, and it's down. I suppose we could put that together and give an answer here for part A as 5.57 times 10 to the negative 11 newtons per coulomb in the negative, I'll put the negative out here, J hat direction. So that might be a good answer for part A. Whereas part B would be the same logic. So we're going to end up with the same formula. I would say, okay, it's the magnitude of the electrical force has to equal the magnitude of its weight. The magnitude of the electrical force is the magnitude of the charge times the magnitude of the electric field times mg. And so the magnitude of the electric field is mg over the magnitude of the charge, although we're dealing with a positive charge here. So let me just drop the absolute value here. And now I can get the magnitude by doing the same math here. It would be the mass of the proton, that's the 1.67 times 10 to the negative 27, times the 9.8 divided by the charge, 1.602 times 10 to the negative 19, and then coming up with a 1.02 times 10 to the negative 7. And again, same unit discussion. The numerator would have newtons and the denominator would have coulombs. So this would be newtons per coulomb. And that's probably a good enough answer. If we wanted to, we could put it in a vector form like we did in A, and then just call this J hat. So there's its magnitude and there's its direction. Makes sense that we need a bigger field than the electron because we got to supply a bigger force because it weighs more. Yeah. Big thing though is this field has to be down in A and this field is up. All right. Well, I hope that was helpful. And I'll switch back over to the chat. Let me just scan here real quick. Anybody from 121 put anything in there? Okay. I don't see anything. All right. Let me just say it again before I move on. We're in the priority time for the 121 people. So if any of you are around, got a question, throw that in the chat. I'll move you to the front of the line. But in the meantime, if no one does, we'll get to you 122 people because you guys have been hit with some hard material right at the beginning. You're in the middle of the book, and some of the hardest stuff is in the first chapter. Whereas 121 people are starting with the easier stuff, and 102 people they're each starting at the beginning of the book. All right, so I'm going to go on. I don't see anything in the chat there, so I'm going to go to next one in the chat by Johnny here. Number 47. Let me just do a little math. This must be 33 minutes into the recording. So when I send out this recording, I can have some kind of rough approximation for people they want to just see that one. All right, so I'm just going to put here at the top of the page in case anybody scans the video kind of quickly. They can see that this is from chapter 23 and it's problem number 47. All right. Johnny, let me find that. Get my other screen going here. 47 says the following. 4 identical charges, each are equal to 10.0 microcoulombs, are located in the corner of a rectangle as shown in figure 47. So let me just transfer that figure onto my scratch pad here. So here's the rectangle. They put these charges of Q. Let me just go back. Did I read they were all the same charge? 4 identical. Yep, 4 identical charged particles. So Q is equal to a plus, so we know they're positive, and they're 10 microcoulombs. All right. We're located in the corners of a rectangle as shown. The dimensions of the rectangle are, so they give the length here. So L equals Now they say 60 centimeters, and I'm just going to do a quick unit conversion in my diagram. Let me put that as 0.60 meters. I have a feeling they're going to ask something about electric field or electric forces. And there I'm going to need Coulomb's constant. And Coulomb's constant is in the units of meters. So for that matter, maybe I should do the same here with the charge, because Coulomb's constant is in units of coulombs. So maybe I should also write the charge in coulombs and get rid of the micro. So it's 10 times 10 to the minus 6 coulombs. Since micro means 10 to the minus 6. And by the way, as a note in passing, all these prefixes you may not have memorized. They're back into chapter 1 of the Survey book, or even chapter 1 of the OpenStax book. They list all these prefixes of the metric system. I think they're also in the front cover of the hardcover of the book, but on the PDF, they're like in the first couple of pages. So you might want to know where those prefixes are, because we use some that aren't as common, like nano and micro. The other ones like centa and milla, killa, you're probably familiar with, but and maybe even mega. But then we get to giga and tera and alta and pico, and people see pico and they go, pico, what the heck's pico? So know that those prefixes are there, and you may have to go back to chapter 1 to kind of look those up. All right, so that's what micro is if you didn't know that one. Centa, I think you knew. And then let me keep reading here. The width is 15 centimeters. So I'll put width and put a little diagram here. And that's equal to 15 centimeters. But again, I'm going to go ahead and put that in meters. Because again, I have a feeling I'm going to be doing a Coulomb's constant here. And maybe I should have read the whole thing, so I know if I'm going to need it or not, but I think so. So it says calculate the magnitude and the direction of the total electrical force. Well, there it is. They're after electrical force. So, yep, I'm going to do Coulomb's law here. Exerted on the charge at the lower left corner by the other three. All right, so lower left. Maybe I'll just circle that one. I'm going to get a different color here. So we're looking for the force on this. Okay. Now, in case I didn't get it clear in the lecture, I know I haven't said this in the review here today or the help session today. So I feel like I should say it now. The idea here is to find the total electric field by adding up electric fields from individual objects. The purpose being this, that if you wanted to know the total force, you would take the charge and multiply it by the electric field that is made up by the other charges. And I want to be careful here. That can get confusing. So what I'm saying here is the electric field at this point is created by these three. And I'm going to take the electric field that is created by these other three and add them together to get the total field at this point, and then multiply it by this charge. So if I were to label these as like charge 1, charge 2, charge 3, and charge 4, the logic is this, that I am going to add up the electric fields from 1 to 3. So it's the charges 1, 2, and 3 that make a field over here. And the combination, the vector combination of these three makes the total field. And then I multiply it by the charge that I put there. So this here would be charge number 4. Okay. And so I like to do a little diagram, and I think you saw it in the video lecture, that to get force, you get that from the field. Maybe I should put an arrow that way. And I should say total field because that comes from the sum of the individual fields. Actually, I think in the diagram I wrote it because it's a springboard of Physics 121 is remember from Physics 121 that if you have acceleration, you can get velocity, and from velocity, you can get position, and you can get acceleration from force. And so now I'm trying to say you can get force from the sum of the electric fields that is equal to the total field. So that's really kind of my thinking here in this diagram, where if I were to say, circle this, this is our lessons from Physics 121, and this is what we're learning now in Physics 122. And this problem only has us go this far. This one has, say, hey, figure out the total field, and from the total field, get the force. Now, if they had given us the mass, then we need to get the acceleration. And there's a few problems like that. I remember doing those on the first Zoom session. We did one. We needed the acceleration in 41. We needed the acceleration.
I think it was problem 41 that we did together.
Yeah. Okay, definitely 41. But I thought there was a second one I needed acceleration in too. And I'm sure there is, but I shouldn't spend more time looking for it. But there was two where we went the next step to get acceleration, and then the next step to get velocity, and the next step to get position. And so we continued along this chain that we hopefully haven't forgotten. Although don't feel bad if you have got a little rusty on it, because that's kind of the thinking of this course is that if we throw in this chain of events periodically, this will help you kind of solidify your lessons from 121 as well as learn the new stuff here. But I digress quite a bit from this problem. So let me go back to this problem. This is what I'm after in this problem. So I'm going to start here and add up the electric field from the three individual ones to get the total. And then once I get that, I'll just multiply by the fourth charge to get the fourth force. All right, so let me go to another page, but keep this one handy because I think I'm gonna have to keep coming back a lot and pointing at this picture here, okay? So let me do this. Let me say, okay, so what is the electric field from number one? And so let me come back to the picture. So here's what I'm really asking. I'm asking, what is the electric field at this place right here where charge number 4 is from number 1? And that's where that famous Coulomb's constant times the charge, and I'll put charge number 1 divided by R squared comes into play. And at least that's the magnitude. So Coulomb's constant is the 9 times 10 to the 9th, and the units are Newton meters squared over Coulomb squared. Now the charge I'm talking about, so let me come back to the picture here, that it's about charge number 1 and the field this one makes at this distance away. So the distance away is the width of it. So the charge is the 10 times 10 to the minus 6 coulombs. In fact, they're all that. That's what we wrote down earlier here. This is the charge of every one of them. So charge number 1 has that amount. And the distance away is the width of the rectangle, the 0.15. So this would be 0.15 meters and squared. And if you look at the units for a moment, you'll see that meters cancels with meters squared, or meters squared cancels with meters squared. That's why I had made the comment earlier that there's a good chance that we're going to want our width and our length in meters, because I think I'm going to need Coulomb's constant to do this. So that was a good guess on my part here. Okay, and then notice also one of the coulombs from in this Coulomb's constant cancels with one upstairs. So I'm going to be left with newtons per coulomb. And that's good because that is the units I want for an electric field. So now grabbing my calculator, I can go 9 times 10 to the 9th and multiply it by 10 times 10 to the minus 6. And I can divide that by 0.15 squared, and I get 4.00 times 10 to the 1, 2, 3, 4, 5, 6. So this is 4 million newtons per coulomb for that electric field. Now that's the magnitude. Maybe I should come over here and give a direction. So let's see. If I realize that for positive charges, the field points away, the field from number 1, so let me call this E1. I'm going to dry here. E1 is this one right here. Okay. So that's kind of my first. What is the electric field from number 1? Let's go to number 2. Now, number 2 is a little harder because how far away is it? It's along a diagonal. But nonetheless, I'll do the same logic. And so the magnitude of number 2 is Coulomb constant times charge number 2 and the distance away squared. So 9 times 10 to the 9th Newton times meters squared over Coulomb squared. So there's Coulomb's constant. The charge of number 2, well, they're all the same at 10 times 10 to the minus 6 coulombs. Okay. Now distance away is going to take some work in terms of Pythagorean's theorem. You'll write that in green. But remember then, if we take this width squared and the length squared, we get the hypotenuse of a right triangle squared. So that means if you take 0.15 and square it, so there's the width, and you add it to 0.60 and square it, you are going to get the distance squared. Perfect. That's what I want, is distance squared. All right, so coming back to my math page here, I'm going to put 0.15 and square it, and add 0.60 and square it. That is the distance squared. And that's what I want. I want distance squared, not just distance. This is not the distance. I don't square this. This is distance squared. And of course, I did everything in meters and squared it. So in terms of units, meters squared cancels, one of the coulombs cancels, and we're going to be left with newtons per coulomb for the unit. And then let me grab the calculator. Now, if it'll be okay with you, I'll save myself a little bit of time, and I'm just going to hit re-enter. And that will just repeat what I entered before, because see, the Coulomb's constant is the same, and the charge is the same. What's different, though, is what's in the bottom. So I'm going to insert a parentheses, and I have the 0.15 squared. I'm going to add to it the 0.6 squared. I'm going to close parentheses. So hopefully I was showing you a way that if you're not talking about it, it goes pretty quick. But talked about it there. So probably should have just could have re-entered them. Anyways, so I'll hit enter with that. And let's see what I get. I get 2.35 times 10 to the 1, 2, 3, 4, 5. Okay. And it couldn't hurt to come back and compare it to number 1, because we do have the same charge, but we're quite a bit further away. So we would expect it to be quite a bit smaller. And it looks like it's about 200 times smaller. I mean, 20 times smaller, because that's 10 times smaller, and then that's about 2 times smaller. So I think I did that okay. All right, so let me try the third one. All right, so KQ over R squared again. I'll come back to the picture, but here's number 3. I'm trying to find out how much field does number 3 create at this point where number 4 is. So the distance away is the length of the rectangle, and that's the 0.6. So I'll put in the Coulomb's constant, 9 times 10 to the 9th. And I'll just drop the units this third time. You see from the other two, the units do work out in terms of newtons per coulomb. So then I'll put the charge as 10 times 10 to the minus 6 coulombs. And the distance is the 0.6 and squared. And then coming back to my calculator, maybe taking that little shortcut again, I'll just go re-enter. And I think if I just go backwards and delete what I don't want, I don't know if that's better. Ooh. I think I got it. I don't know if that was better or not. But anyways, I just want downstairs the 0.06. Maybe I'll scroll over, make sure I did it all right. So there's Coulomb's constant, blah, 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 and hit enter. All right, so this would be 2.50 times 10 to the 1, 2, 3, 4, 5. And again, this one, I guess I would expect it to be smaller than number 1 because we're further away. Number 3 is further away than number 1, but number 3 is closer than number 2. And so this field should be a little bit bigger. And sure enough, it is. So, all right. So I'm thinking these are correct. They seem correct. And let me then, finish this by saying, all right, so here is the total electric field. I've got to take electric field number 1 and add it to electric field number 2 and add it to electric field number 3. And so just to go back to what I said at the beginning, this is my strategy, finding the total electric field. I get the total electric field by adding up the electric field from the 3 individual pieces. Okay. And then the last step is the easy one. To get the force, you just multiply by that charge. Okay, so maybe I need to come back to the picture because I just realized in the picture, I only talked about the direction of number 1. I did not talk about the direction of number 3 or number 2. Now, they're all positive charges, so they would be away. So number 2 would be in this direction. So I'll call that electric field number 2. It would be angling down at this direction. And then number 3 would begin straight away from number 3. So it looked like this. And so this is electric field number 3. So these are my 3 electric fields that I have to add. And the number 1 is only on the y-axis and number 3 is only on the x-axis, but number 2 is a little trickier. So let me just get an angle here. Maybe for the moment, I'm just going to call it angle theta. But before we finish the problem, we need to probably get a number for that angle. And we could do it now, but I wanted to kind of focus here on this electric field, because I would say this, that electric field number 1 is 4.00 times 10 to the 6th newtons per coulomb. And as we talked about in the picture then, it would be in the negative j hat direction. So that's the electric field from number 1. Okay. Let me go on here to say, okay, what is the electric field from number 2? Now, number 2 is the harder one, because number 2 has components both x and y. But I can see here that it's negative x and negative y. Okay. All right. So let me take the magnitude from number 2 we did earlier and go 2.35 times 10 to the 5 newtons per coulomb. And if I multiply it by cosine of theta, so cosine of theta, that would give me the x component of it. And so that would be a negative I hat. Oops, get that back on the screen. So that's the first component of number 2. Let me do the y components of number 2. So again, kind of going back to the math we learned in 121, right? It's magnitude times either sine or cosine, depending on what you want. And so I want cosine of theta for the x component, and I want sine of theta. So there's sine of theta, and that would give me the y component. But again, let me emphasize, that is pointing down. So we've got a left component and a down component for number 2. So that's the harder of the 2. So the electric field from number 2. This up here is the electric field of number 2 in the x direction, and this right here is the electric field of number 2 in the y direction. Hang on a second. My dog was barking at here. If it was anything important, I think maybe I just got a package or something. So I'll leave that alone here for a while. Okay, so the third piece of this is the electric field from number 3. And so let me put in the number 2.50 times 10 to the 5th newtons per coulomb. And let me come back to the picture here. Number 3 is pointing in the negative x direction only. So negative I hat. So that means when I do my vector addition, I would put these together. These are all the j hats, and I'd put these together. Now I can't do a calculation until I figure out what theta is. So let me come back to my picture here and see if I can figure out theta. Now, maybe the first thing to do is to realize that these are called vertical angles in my geometry class. So I call that theta. This is theta. Now with theta here, I can see that tangent of theta is the width over the length. So that's 0.15 over 0.6. And that will give me a way to get theta. So turning my calculator back on and checking, am I in degrees? I am. Let me go inverse tangent of 0.15 divided by 0.6. And so we're looking at about 14.0 degrees. Okay, let me go back to page 2 here. This might get kind of long. I better number them so I don't get too lost. So let's call that number 1, and the one we're about to get to the end of, let's call that number 2. All right, so back in here, I need to remember that this is the sine of 14 degrees. So I'll just do these two. These are the j components. So this is 4 times 10 to the 6th. And let me not worry about the negative j hat for a second. I'll just put that at the end. So I'm going to go that added to 2.35 times 10 to the 5th times the sine of 14 degrees. So this comes out to be 4.06 times 10 to the, I believe that's a 6. 1, 2, 3, 4, 5, 6 newtons per coulomb in the negative j hat direction. Okay, so that's the total field going down. And you can see that it's really dominated by number 1. I mean, that's almost all of it. Number 1's real close. So I bet when we're all done here, whatever field we get is really very close to just number 1 by itself, because number 1 is close, much closer than the other 2, even though there's 2 of them. And the second one kind of adds to the down. That's what that 0.06 came from, because number 1 was just 4. Okay, and then also over here, let me take the field here, which would be 2.35 times 10 to the 5th multiplied by cosine of 14 degrees. And add to it 2.5 times 10 to the 5th. And get 4.78 times 10 to the, and this must be a 5. 1, 2, 3, 4, 5, yeah. And this would be in the negative I hat direction. Now, again, let me not box it, but I'll circle it. This, I think, is the lion's share of the work right here. This is the main part. This is what is the electric field. Now, I'll need another page to finish this, but this is a good chance for me to say something bigger than just this problem. This is the idea of this chapter, is figure out how to get the total electric field by adding up the points, in this case, 3 of them. And once you get that, the last step to get the force is pretty easy. Just take the charge that's in that field and multiply them together to get that force. So, well, we got to do our last step. All right, so our last step would be to say that the force is equal to charge number 4 multiplied by the total electric field. And again, let me emphasize, when I say total, what I mean is the total made up from the other 3. All right, and that's what we just did here on page 2. So this right here would be charge number 4. And they're all the same charge, 10 times 10 to the 6th coulombs. Oh, minus 6. Yeah, minus 6. Okay. And then times the electric field. Now, if it'll be okay with you, since it's tradition to write the x component first and then the y component, and just the way I worked mine out, I kind of got them in reverse order. I'm going to put negative 4.78 times 10 to the 5 I hat for the x component, and then minus 4.06 times 10 to the 6th for the j component. So they're both negative, the negative I hat and negative j hat. And they both have the units of newtons per coulomb, which is really good because the coulomb will cancel off. And when this is all said and done, we'll be in units of newtons. Okay. Now, fortunately, I think I can do this math in my head. This is 10 to the minus 5. When I put that here, that becomes minus 4.78 x hat or I hat, because that minus 5 and that cancel. And then this becomes 4.06 times 10 to the 1, which maybe I should write as 40.6. And then that's the j hat direction. And let me just come back to the question, because this is the force in components. They may be asking me for the magnitude of the force. I am not sure if they want components or they want magnitude, but I'm feeling like I'm done. Let's calculate the oh no, there it is. Calculate the magnitude and the direction. Okay, so they want magnitude. So, all right, I got another step to make. We know from Pythagorean's theorem that the magnitude of the total force, right, is the x component squared added to the y component squared, and then taking the square roots. All right, so I got the x component, I got the y component. And by the way, notice the y component much, much bigger than the x component. This thing is dominated by that first charge, pushing way down on it. All right, but getting the x component here, 4.78, and squaring it, and then adding it to the y component, 40.6, and squaring it, and then taking the square root. It's still going to be really close to just the y component. That's dominated. And so it is 40.9 for the magnitude. So this little x component made the magnitude go up just a little bit bigger than the y component. But for the most part, there's the force. And direction is pretty easy. That's the other half of this. Because the direction is the direction of the field. Maybe I should write that again. Force would be equal to charge number 4 times the total field. And so this little equation is saying that if you have a positive, and I think we mentioned this on the other one, if you have a positive number here for the charge, which we do for this problem, then all you're doing is changing the size, but not the direction of the electric field. So electric field, electric force are in the same direction. And if the charge is negative, as we had for the electron in the other problem, then you would be multiplying by a negative number. So then the force would be opposite of the direction. So really, you just need to figure out what the direction of the field is, and that can lead to the force, because it's either in the same direction or opposite. And in our case, it's same direction. So let me find the direction of the field. So let me bring page 2 back into this picture here and say, okay, remember, this is what the field looked like. So if I did a grid here, it's saying it goes down by this much, 4.06 times 10 to the 6th. And it goes to the left, see the negative I hat, left, down, negative j hat, by a much smaller amount of 4.78 times 10 to the 5th. So when you add a big down and a little left, you're going to get a direction, something like that. And this angle won't be very big. why don't I call this angle phi? I want to stay away from theta because I used theta earlier back in the figure to say theta is the angle of this diagonal. And of course, that is the angle of electric field number 2. That is not the direction of when you add them together. You can see by the time you add them all together, it's something like that. So the direction of the total is not the direction of number 2. And so it's not an angle of theta. And I don't want to confuse you using the same symbol. So let me not use theta. Let me use some other Greek letter, and kind of tradition is to go to phi. Okay. All right. Wow, this one turned out to be longer than I anticipated. I'm on page 4 here. But now I can say that the tangent of phi, and maybe I should just say the magnitude of the tangent of phi, looking at the picture, is the magnitude of this opposite, 4.78 times 10 to the 5, divided by the magnitude of the adjacent. Just, can I copy these down right? Yeah, 5. Okay, good. All right. So you can see that the vertical one down here is about 10 times bigger than the horizontal one. So the magnitude of phi is not very big. So I'm going to go inverse tangents, 4.78 times 10 to the 5th. And I'm going to divide it by 4.06 times 10 to the 6. And as I said, not a very big angle. It's only 6.71 degrees off of straight down. So maybe I should put there's different ways to write this, but maybe I'm going to say 6.71 degrees left of straight down. If we kind of use the traditional mathematical idea of an angle measured from the x-axis, I guess we would go all the way around, which is 270 degrees, and go back 6.71. What's that come out to be? 270 minus 6.71. And so you might call it 263.3 degrees. Usually when we measure things from the x-axis, then we don't say anything. It's kind of the default, but I'll just say from the positive x-axis. And then maybe I'll even say with counterclockwise being positive. And again, that's the tradition. So normally you don't say anything. That's kind of the way it's assumed. But I got to admit, this is not very helpful to me. To tell me that the angle is 263.3 is not very helpful. What's very helpful to me is it's slightly left of straight down. It's 6.7 from left of straight down. That would be very useful, even though it's not the kind of conventional grid. So I really like this. Well, told you it was a long problem. Hope I didn't bore too many of you too long there. But let me just to see if I fouled up anywhere, jump over to the solutions. This was what, number 47. Let me scroll down. Your author says the magnitude is 40.9. Good, that's what I got. And says the angle, and he does it from the 263. So he does it all the way around the positive x-axis. Okay. Nice. Very nice. I like that. All right. And who was that for? Oh, that was for Johnny. Johnny, I hope that helped.
Yeah, thank you. That's great.
All right. Good. Hopefully not too long-winded. But I probably don't need to tell you guys, but you're probably experiencing that it does take a long time, even, in fact, I kind of sometimes judge that. I mean, if I was doing it without explaining it, I could do it much faster, but taking the time to explain it is usually about the same time it takes the students to do it. So if it took me 40 minutes or so to do a problem by explaining it, it'll probably take you 40 minutes to work it out and think it out on your own because you're kind of working it out in your head. All right, good. Let's see, where are we? Okay, I'll go back to the chat room. All right, well, I don't see another one thrown in the chat. If you guys have one or, oh, yeah, and I wanted to ask Shasha, oh, looks like he walked away, but maybe I'll ask the other two of you, but did you guys see some of these solutions I sent out by email?
I did, yeah.
You did? Okay.
Was it the solutions for the homework?
Yeah, I call them video solutions. And then I guess what I really want to say is if you don't know, if you're only looking at Canvas, and maybe I should try to post those emails on Canvas too, but it's just really easy for me to make a video solution and send it out. And so I sent out like 6 video solutions for this chapter. And so if you don't know that, I wanted to tell you that. So check your pipeline account. So that's, I guess, directed at the 3 of you. I think you're all in 122. All right. So, Brendan, you got one, number 16. Okay. So, chapter 23, number 16. Let me write this in my little notes here. Number 16. And let's see. We started. Ooh. Oh, it's like 1 hour and 16 minutes ago. Should be about an hour 16. Okay. All right, let me try. Turn off these messages here so that well, I'm all using my phone. These messages don't get in my way here. All right, let me come back to 16. And I was trying to remember if this was one of the video solutions I sent out, if that would be helpful, but I don't recall. So I was going to work through it again. I know some of the ones I've done here today were in the video solutions, and some weren't. So some are new and some aren't. But I just wanted to tell you guys, keep a close eye on your email throughout the week. As students ask questions, I usually kind of work through them just like this on the video here, and then send it out. Of course, it's not a Zoom recording. It's just a regular YouTube recording. All right, so let me try number 16. 16 says you have two microcoulomb particles located on the x-axis, one at a +1 meter and the other at -1 meter. All right, so let me draw a little picture. And so let me come to a +1 meter. And on the x-axis, and how much did it say it was? Number 16, a 2. And let me write it as a microcoulomb, but let me write micro as 10 to the minus 6. And then at negative 1 meter, oh, we have the same thing, 2 times 10 to the minus 6 coulombs. So a lot of times in nature, these are equal in magnitude and opposite. It's called a dipole. This is not very common in nature, but if they have the same charge, it's a bipole. Well, I shouldn't say it's not common. Depending on how you look at it. Anyway, so a bipole. Anyway, so looks like we have a bipole. We have 2 equal amount of same charges separated from a center point, in this case, the origin. Okay. And they're separated by this case in 2 meters. All right. Now it says determine the electric field on the y-axis when y is 1 meter up. So, okay, so we'll go up about here and say, okay, what is the electric field there? Now, before I do too much work, let me call this, say, number 1 in the positive x-axis and charge number 2 on the negative x-axis, because number 1 is a positive, and so it would make a field pointing away. And so let me call that electric field number 1. And this over here, let me call this field number 2. Now, this one's going to turn out to be a lot simpler than the last one we did. Let me go back to the picture of the last one we did. The last one we did, to get the total field, we had to take field 1, add it to field 2, and add it to field 3. This is easier for a lot of reasons, but it's the same idea that I'm going to get the total field by adding up the field from 1 and field number 2. So what makes this one a little easier than the other one is I've only got 2 electric fields to add together. So that's a little easier, but it gets better than that. Look carefully at this. You can save yourself a lot of work if you notice symmetries. And so besides doing the math, make sure you do the physics, okay? And so if I were to look at, say, field number 1, I would say it has a left component and an up component. So those are the X and Y components of number 1. And then likewise, number 2 has a right component and an up component. And if you think about what you are going to do to calculate the field, you are going to look at, let's say, to get the field number 1, you're going to look at how far number 1 is away and at what angle. But if you compare that to number 2, notice it's the same distance and the same angle. And so as a consequence, this field going left and this field going right. So the horizontal field from number 1 and the horizontal field from number 2 would be equal in magnitude, opposite in direction, and therefore cancel out. So the good news is we could just come right down here and say the field in the X direction is going to be 0. We don't have to spend a lot of time going through a lot of work. We don't have to do as much as we did on the last time. And that's why I was saying this one is set up to save you a lot of work. This is not nearly as hard as the number 47 that we just did. I don't even have to mess with the X component. And it gets even better. Look at the Y component. Same logic being that this vertical Y component for number 1 and the vertical, that is the Y component of number 2, they are the same. So I would say that the Y component is twice the Y component of number 1. And so what I'm trying to say is you can save yourself a lot of calculation and a lot of time if you realize that. I don't have to do X and Y component of both of these and add them all together. I only have to do a Y component of number one. So what looked like I had to do 4 calculations to get X and Y of each of them, I only have to do 1 calculation, which is to get the Y component of number one. That's a beauty of this problem. And what I want to emphasize before I actually dive into just plugging and chugging in the mathematics is to say, make sure you see the physics, make sure you're reading the math and what does each of these mean along the way, okay? So that's how I'm going to say that, all right, I'm going to make this problem very simple on myself because I know that the electric field total then is going to be twice the magnitude of the Y component of number one, and then it's all up. And so this boils down to finding the Y components of number one. All right, so let me do that. The Y components of number one, and so let me come back up here to the picture. And let me put a little angle here, call it theta, would then be the magnitude of number one multiplied by sine theta. And the magnitude of number one would be Coulomb's constant times charge number one divided by distance squared number one. And so I'm going to put those in. I might want to do a little side calculation and figure out, you know, the same as we did before. What is the distance away and what is the angle? I'll start with the distance away. So let's start with Coulomb's constant, 9 times 10 to the 9th. And since we've done a lot with the units, we know this comes out to be newtons per coulomb. So let me not put in the units here this time. But there's 9 times 10 to the 9th. The charge of number one, as we said earlier, is this 2 times 10 to the minus 6. Now, the distance away is coming back to the picture from charge number one to where I'm trying to find the field. And they said this was 1 meter. And I was trying to find it at a ½ meter up. So using Pythagorean's theorem, this would be 1 squared plus 0.5 squared. And that together is the hypotenuse squared. So there is the r squared. And then it'll be sine of the angle. All right, well, let's come back to the picture. This is a lot like we did with the rectangle. But this angle right here, theta, inside of this triangle would be the same as that one. I guess we would call these in geometry corresponding. And so if I look at the green one and say the tangent of theta would be its opposite, 0.5, over its adjacent of 1, would give me that angle. All right, so putting my calculator back on and saying inverse tangent of 0.5 divided by 1 is 26.6 degrees. So this should be the sine of 26.6 degrees. All right, so we go to a page 2 here. Try to keep this on the screen. You guys can see it. But now I need to punch in all those numbers. And as we said many times earlier, that comes out to be units of newtons per coulomb. Okay, so grabbing my calculator, this is 9 times 10 to the 9th times 2 times 10 to the negative 6 times sine of 26.6 degrees. Maybe I'll just hit enter. So there's the numerator. Then divided by, and I got Pythagorean's theorem here, 1 squared plus 0.5 squared, close bracket, enter. And so it looks like 6.45 times 10 to the 3 newtons per coulomb is the vertical component of number 1. So now we can finally finish the problem. Remember, we just got to multiply it by 2. And so the total field would be 2 times that. So times 2, which would be 1.29 times 10 to the, that must be 4. 1, 2, 3, 4 newtons per coulomb in the vertical direction. I was thinking there might be a part 2 to this. So that's A, yeah, determine the electric field. And then B, and actually let me check A before I go a little further. I see we're getting to our end time here. Like my son's calling me back. I'll get him in a second. Let's see. Number what? 16. Uh, 1.29 times 10 to the 4th. Good, good. So it matches the answer. Good, good. All right. And then part B is actually, again, the easier step. Remember I said, here's the big step, that to get the total field, this is what we did in A, you add up all the fields from the individual pieces. Now then, to get the force, you take whatever charge you're going to put there and multiply by the field that's been created by those other charges, which would be these two. So that's what B is saying here. It's saying calculate the electrical force on a -3 microcoulomb charge that is then placed at this position. So I would say then the force is, and so I'm going to put a -3 microcoulombs, although I'm going to write the micro as a 10 to the -6. So there's the -3 times 10 to the -6 for the charge, times the electric field, which we just said here was 1.29 times 10 to the 4th newtons per coulomb in the vertical direction. Notice, by the way, then we're going to get a negative j hat direction, right? Because the negative here is what's going to make this a negative, and then the j hat, and that's what I was saying here. Our field is up, but our charge we're going to put there is negative. So the force is opposite of the direction of the field. Field is up, force is down. And then also notice that the coulombs will cancel off. And so we'll have force in newtons, as we should. And so the final step is to take that electric field and multiply it by a -3 times 10 to the -6. And we get a -0.03, and I'll do 3 significant figures. Let's go 69. And got the same answer that the author got. Awesome.
If the field is pushing up, then why is the force pushing down on it?
No. The field is pointing up. The force is down.
Okay.
All right. I'm going to say that again. It can get a little tricky to understand, but an important lesson to learn. Look at this equation carefully. Okay. If the field is pointing to the right, so here's the field. And just for a number, let's say it's equal to 5. That's a plus 5 because it's pointing to the right. If your Q is positive, greater than 0, and just for the sake of a number, let me say it is 2, you're going to have a positive number multiplied by the field, which would leave you with a positive number. So the force would be a 10 and it would be positive. So the field and the force are in the same direction if it is positive. But if it is negative, the direction of F, let's just say -2. You take a -2 times a positive 5 and you get a -10. So please never say that the field is the direction of the force.
Okay.
There's a direction to the field and there's a direction to the force. And so in what I kind of just described is the field is to the right. And then if I put a positive, it would be pushed to the right. But if I put a negative, it would be pushed to the left.
Okay. That makes sense.
Yeah. And so force and field are mathematically connected. They're not equal to each other, and they're not in the same direction. See, when you multiply the field by that number, that changes that number. And since this number can only be positive or negative, in terms of direction, it can only be in the same direction or opposite direction. And in terms of size, it could be any size because Q can have any value it wants. So that's why, notice this chapter is titled Electric Field, because what's more important is the electric field. Now, ultimately, we want the electric force. I get that. So the hard part is get the field. But the neat thing about it is the field has nothing to do with what direction the positive or negative is going to be moving. So it's nice to talk about what direction the field is. And you don't have to say, well, did you put a positive or did you put a negative in the field? Well, it doesn't matter. The field's the same direction. It's when I put a positive or a negative in there is when it moves to another, either left or right or up or down. But the positive and negatives move in opposite directions. And so this makes electrical forces harder to deal with than gravity. Gravity, it always pulled one direction. It didn't matter what you put there. You could put a car, a boat, or a plane, and gravity pulled it down. But here, we would have to say, well, it depends what you put in the field. And so if you put a boat,
after looking at that graph for a sec longer, that actually makes more sense now.
Yeah. Okay. Hey, good. Hey, well, I don't want to leave you guys hanging too much. It is time for our break. Also, as I think I mentioned, I don't think I said why, but it's my dad's 88th birthday celebration. His actual birthday was a little while ago, but finally get a chance to celebrate it. He's a big Dodger fan. So we are going to go to Dodger Stadium. That's why I needed to leave a little bit earlier if I can get all the way down to LA and in traffic in time for the game, and actually a little early so I can see batting practice. So that's the reason I needed to cut out our third session. So note that normally there would be a third session. Oh, good. Shasha, you're back here. You were gone a little while ago when I was telling the other two, make sure you check your Pipeline account because I have sent out a lot of video solutions and I didn't know if you knew that. Okay, you do? Okay, you should. Okay.
Just through the email?
Yeah, and that's on the Pipeline account.
Okay.
Yeah, and so some of the solutions are ones we did today and some of them are ones we haven't done today. So that could be helpful. But also in that email, I explained how I wouldn't have time for a third session today. And I promised you guys 3 things. One is I promised you I would send out, and I already did, So check your pipeline account. The Zoom of the same discussion last year. So there's 3 of them, and I highlighted the timestamp of what we did, what problem. So if you haven't got a chance to look at your pipeline account, do that. There's 3 more Zoom sessions recorded from last fall, and I label which ones we did and which ones are related to your class and which ones we did. Some of those are what we did today. Some of those are what I sent out. So can't hurt to double or triple do them, but you might want to see them. Let's see. The second thing I promised is I said, if there were any questions left in the chat after the second one, I'd write them down and do a solution to them late tonight or probably tomorrow. It's going to be real late when I get home. So tomorrow, and I'd send those out on pipeline. I don't see any, but if any of you want to shoot one off, do it now, or you could do it later by email. Same thing. If I see any questions in my email tomorrow morning, I'll make a quick video of those and send those to you. What was the third thing I said? I said if there was still a lot of questions, why I would set up something for the weekend, but I don't see that, so I'll pass on that.
Just a general question: is the homework going to turn graded on correctness, or?
No, not on correctness, on effort. Yeah.
Okay.
So make sure you work hard on these. The idea is to learn. If you do something wrong, don't worry about that. Also, the whole reason I gave a due date not until the test is because I know this first assignment is brutal, and usually only half the students, if that, are able to do the whole assignment by Sunday night. But I would love to encourage you to do it by Sunday night. You should continue to try to do it by Sunday night because we're going to have other chapters starting next week. So you don't want to get behind, but at the same time, you don't want to skip a problem just because it was hard and there's a due date. I don't want you to do that. We'll work on it. It's totally worth it.
Michael, then I remember you saying in the lecture that chapters these 23, 24, and 25 are going to be pretty difficult. So how bad are 24 and 25 compared to this? Is it, or in terms of like spacing it out? Maybe.
So 22 and 23 are about the same caliber. Maybe a hair easier because 23 is maybe 24 is a hair easier because you're kind of getting the feel for it. This is a wake-up call, and you've learned a lot this week. And it's like working out for a week. You can do the same workout the second week, but it's going to feel a little easier because you've built up some strength. And so I would say that. But I would also say 25 truly is easier than 23 and 24. Okay. We do a lot less vectors in there. And that's why it's easier.
For sure. Yeah, I was wondering because
we still do a lot of calculus though.
Yeah.
So notice I didn't say easy. I said easier. Yeah.
Easier for sure. I mean, it is 122. So
yeah.
But
and then 26 before the test is the easiest of all 4 of them. So that's good to hit that easiest one when you have the least time to learn it too.
Okay, cool. Yeah, I was just trying to time myself because I heard that 23 was going to be the hardest. So I did a little bit before the semester started, when you sent out the reminder. And now, I'm trying to finish this problem set by today so that maybe I can, start reading into the weekend. You think that's a good idea?
Yeah, that's a great idea. Yeah. Okay. That would be a huge benefit of why you started early. Yeah, and you would reap that reward.
Yeah, I will. Okay, well, thank you.
All right.
Have fun with your dad. That sounds really fun.
Yeah, it's 15 of us, so it should be a big group here.
Oh, wow, nice.
Oh, you. All right, let's see. So I'll say bye, Johnny, and unless you got a question for me, and we'll head on out here for today. But keep your questions coming; they're great.
Yeah, I'm good, but thank you so much, and enjoy your time.
All right. Take care.
Thank you, Professor.
All right. See you soon. Don't hesitate to send me an email anytime.
Will do.
Okay.
All right.